Hello, everybody. Thanks for the invitation for being here. Thanks for being here in the audience. This is what I'll be talking about, carbon sequestration. As Jean-Louis mentioned, this is what I'll be talking about is something that we've been doing in practice in Portugal, but that immediately applies to any other country with Mediterranean conditions, so quite broadly applicable. And in fact, I would say many of the aspects apply across the board for, well, around Europe and even around the world. So what we've been working with is a system which was developed since the 70s in Portugal by an agronomist called David Crespo. It goes by this mouthful of sown biodiverse permanent pastures rich in legumes, but the mouthful is useful because everything means something. We're working with permanent pastures. They are sown. We're not working with natural pastures. They are biodiverse, and this was one of the radical innovations. If you think that David Crespo was working on this in the 70s in a Western country, where instead of sowing one species when you are sowing a pasture, or maybe two, maybe a legume and a grass, he was sowing up to 20 different species of varieties. This is especially important under the heterogeneous conditions we have in Mediterranean countries, where on a single plot you can have very different soil conditions from one place to the other, where you have very different years. You have drought years, you have wet years, you have different conditions in January, you have different conditions in March, and the best way to adapt to this variability is a bit like if you were to devise a good financial portfolio, is that you have this diversity where different varieties adapt to variability in space and time. So biodiversity, and finally rich in legumes. As you all know, legumes are our natural factory for obtaining nitrogen from the atmosphere without needing a fossil fuel intensive process, point one. But point two, which also needs to be very much emphasized, the nitrogen that the legumes are getting from the atmosphere is going to be locked in complex chemical forms, which means that when it goes to the soil, which is what the legumes in the end are providing to the soil, and that's how they are then feeding the grasses with nitrogen, when it goes to the soil, it goes in forms which are much, much less susceptible to nitrate leaching and to nitrous oxide emissions. Okay, so you get this very, very nice landscape, and also this picture also serves to emphasize that a lot of the work we do in Portugal with this system is under silvopastoral conditions, and I think this is what we have in Portugal and Spain. What's called in Portugal the Montado system, and in Spain the Dehesa system, is an excellent example of a silvopastoral system. In fact, as we speak in Europe, it is the predominant silvopastoral system in Europe, and it allows this symbiosis between the trees and the pasture, wherein the trees provide shading for the pasture. And you have to think that under Mediterranean conditions, plant production is essentially water limited. It is not radiation limited. So in fact, the shadow that the trees create is positive for the plants. The plants already have enough solar radiation. What they don't have is enough water, and the shade provided by the trees reduces temperature and reduces water loss. So there is this nice symbiosis between the two things. On the other hand, and very importantly, the lands where these pastures are being sown are lands that have had millennia, and literally millennia, of inadequate soil management practices, because we've been doing inadequate agriculture in the Mediterranean for millennia. And so there's been enormous losses of soil organic matter, and those losses are essentially promoted by the continuous tilling of the soil, essentially to avoid the invasion of shrubs, which is a natural process of ecological succession, but that we want to avoid when we're doing agriculture. Now, this tillage, which is required under normal conditions, destroys the soil, reduces its fertility, and then in itself harms also the trees. So having the pasture allows us to control the invasion of shrubs, which would compete with the trees, which would also constitute a fire risk. So by having these productive pastures, which are more highly grazed, we avoid the invasion of shrubs, we no longer need tillage, and so soil conditions improve, and that benefits the trees. And of course, in terms of the trees that are being benefited, maybe some of you will appreciate the fact that these trees, half of them are cork oaks, and they give the corks for your wine bottles, so that might be something extra you might appreciate. Okay, So, what we've done is we've calculated the change in carbon a long time when we have this system. You have this graph with the two lines. Please first focus on the lower line, which looks like a sawtooth. That is what is conventionally happening in this system. So you have very low soil organic matter, that's 1% average, which increases a bit a long time, but since shrubs come in, fire risk, competition with the trees, then the farmers till the soil, and that's when you see the tooth coming down. And so basically you continuously maintain the soil at a very low soil organic matter level. When you introduce the system of sown biodiverse pastures, the soil organic matter starts increasing for two main reasons. The first one is you don't need to do tillage, so now you no longer have the sawtooth pattern. And besides, the system is much more productive because of its biodiversity and because of its richness in legumes. So soil organic matter increases fast. It increases extraordinarily fast, as you can see, because after 10 years, on average, you get a tripling of soil organic matter from inadequate 1% levels to reasonable soil protecting 3% levels, so a tripling of organic matter, and which leads to also our statement that this system is also doing ecological restoration. We are restoring soils in the Mediterranean which were destroyed by millennia of inadequate agricultural practices. Of course, as time goes on, and you can see that in the curvature of the curve, which is that it saturates. So you don't sequester, you don't increase soil organic matter forever, but while you are doing that during this transient, which lasts a few decades, but focusing on the first decade, we get this average you see over there of 6.5 tons of CO2 per hectare and per year, which is a very high number. Now, the potential for this soil sequestration led us, I'm originally, as was mentioned in the beginning, I'm a professor at the engineering school of the University of Lisbon. This started out a scientific study. Meanwhile, Portugal created something called the Portuguese Carbon Fund, which is, its budget comes from the selling of carbon emission permits to industry, and they open up a competition to do projects in Portugal that would do reduction of greenhouse gas emissions or removal of carbon dioxide from the atmosphere. We created a spin-off, which is what I'm representing here today. That's Terraprima. You see below that Fundo Português de Carbono, and that's who was paying for the project. So we applied to that, and the project ran from 2009 to 2014, involving around 1,000 farmers on a 50,000 hectare area, and with a total of 1 million tons of carbon dioxide removal from the atmosphere paid by the Portuguese government and paid as an environmental service to farmers. I typically speak for longer than I should, and so I've removed some slides that I usually present, and one slide that normally I would present here, I don't have it today, is that I show an invoice. I show an invoice from one of our farmers to bring home the message that our farmers, when doing this, are not receiving a subsidy, they are providing a service, and they have to give an invoice to Terraprima, and they have to pay value-added tax and all of that. So it is a service. The project, I think, ran very well. It was a success. The European Commission also considered it that, and in 2013 it was considered in the World You Like with the Climate You Like contest run by the European Commission as the best solution for climate in Europe in that year. Okay, so, but nothing is always absolutely easy and going easily, and obviously the system that I'm presenting to you also has its downsides which need to be optimized, especially if we wanted to increase its scale. As I showed you, we did it on 50,000 hectares. We could easily do it on 1 million hectares in Portugal. Well, I mean, we could easily do it if we overcome the difficulties I'm going to mention. We could do it on 1 million hectares in Portugal, and we could do it on millions and millions of hectares just in the Mediterranean. And then, of course, with adaptations elsewhere. So, problems. The system being rich in legumes, and it's being placed in areas with poor soils and especially poor in phosphorus. You know, legumes are very needy of phosphorus. And so there is a significant cost, which is a significant downside to the system, which is the costs with phosphorus fertilization, and which leads farmers to start mismanaging the pasture because they wrongly start saving on the phosphorus fertilizer. So we need to improve fertilization levels. We need to optimize such that farmers provide adequate phosphorus for the legumes but reduce significantly their costs with the phosphorus. Second point, and which is in a sense is scientifically and technically something very interesting about this system, because it is managed much closer to nature than you normally do agriculture. And especially this system lives of a balance, of an adequate balance between legumes and grasses. You need the legumes to provide the nitrogen, but if they're providing too much nitrogen, the grasses grow. And since the grasses grow tall and the legumes grow flat, if the grasses grow tall, they'll crowd out the legumes and you lose your nitrogen factory. And the only way of avoiding that is without enough grazing, because if there's grazing, if the cows and the sheep are coming around, they'll graze the grasses down and not allow them to outcompete the legumes. But of course, you can also not have overgrazing. And it's different in a wet year and a dry year. It's different in January. So this, in fact, requires very sophisticated ecological management knowledge to be done adequately, and so that's another problem, what I've called their ad hoc animal husbandry. Then we have a problem that I think everyone in the room who is in the sector faces, which is it is unattractive to work in this sector, and certainly it is a big problem in Portugal. People will rather work for a lower salary in a bank or in a supermarket than go work in farming. And that's a problem. For the system to work, and especially for a system which has to become more sophisticated, we need to attract young people to work in it. So, opportunities reacting to that. Well, optimize fertilization, do knowledge-based animal husbandry, and create highly qualified jobs which are required to do this better way of doing things, but which also make working in this field more attractive. And what we're now doing is what we're calling Sustainable Agriculture 4.0, which we tried to graphically to express here, which is sustainability, so combining in a balanced way the three pillars of sustainability. That's what you have in the center of the diagram, the social, the environmental and the economic pillars of sustainability, together with the whole technologically intensive approach of Industry 4.0, which we've here represented in this cycle of monitoring, modeling, optimizing and acting. And all of this highly technological intensive, I'm just going to give you several examples that we're integrating with our pasture system, and all these different technologies are being integrated into a single approach. So at the monitoring level, very intensive combinations of proximal sensing and conventional analysis with drone flights and satellite data, such that in the future we can have just the information from the satellites, tracking animals with GPS collars so that we know where they are grazing, and so we can optimize where they should be grazing and where they should be moved to. Modeling both the growth of animals and how they react to different compositions of feed, and the growth of the pastures and the dynamics of the soil organic matter. Then optimizing, and optimizing in a sustainable way, optimizing such that we simultaneously look at economic, social, and environmental issues. And finally, which is what you see here in the lower part of this slide, integrating all this into a single software platform that then allows us to give technical assistance to farmers and generate relevant information, and specifically I'm showing you here the use of variable rate technology for the phosphorus fertilization, so that we optimize the phosphorus fertilization such that it is placed where it should be. And with that, I conclude. Thank you for your attention.
Yes, I have a question. Today, I think that almost all the keynote speakers, they have mentioned at least once the relevant role of manure in carbon sequestration. So I think that sometimes we miss also in the, let's say, the last month's discussion, the importance of monitoring the organic carbon in soil. Indeed, there are already some tools that are used at European level. And within them, we have, if I'm not wrong, the Copernicus Sentinel project, right? How do you see these sensors will evolve in the next years? Do you think they are important? Should we take them into account in the next policies? Thank you.
Yes, absolutely. So that's the approach we're taking here of combining massive data that you can get from satellites and drones with field work. The examples you were mentioning are at a high scale for all of Europe, and here we are concerned, so that's just the issue that you need to develop further, because we need recommendations and measurements at the plot level and at the farm level. But in a sense, the approach is similar. What maybe I would emphasize here is this specific methodology you're seeing here is that the satellite, when you go to the plot and farm level, the satellite is too coarse because it has a 10 by 10 meter resolution, and that's why we bring in the drones. And then we bring in machine learning or artificial intelligence, because what we do is we create a statistical model which allows us to relate the drone images with what we measure in the field. Because if I have a cage, a 1 by 1 meter cage, where I cut the grass so I measure what's there, or I make a soil sample, I can see that cage in my drone image, but I cannot see it in the satellite image. So we first create a statistical machine learning model between the field data and the drone image, and then we create another machine learning model between the drone image and the satellite image, because then the satellite image can see what the drone does. So that's a first important step. And another one that I would just like to emphasize is that we're combining all this fancy machine learning techniques, but also with more conventional models that really understand what's going on in the system, which is what machine learning techniques don't do and don't know how to. And that's a very significant component. And as from you, that's how I think we can move forward. I don't think we can just move forward with big data and machine learning. We have to combine big data, machine learning, and models that understand what's happening in the system based on our scientific knowledge.
Okay, so thanks again, Tiago.